This is a lesson on the universal law of gravitation in conjunction with centripetal acceleration with Newtonian force analysis. Again, centripetal acceleration arises because of an object moving in a circle. The velocity vector is constantly changing, therefore we must represent that with an acceleration. The acceleration is v squared over r, which is also equal to omega squared r based on this relationship, which we saw used in the previous lecture. To extend the concept, we can look at the universal law of gravitation. Every particle in the universe, it's true, exerts a force on every other particle in the universe because of their mass. Objects with mass exert forces on each other depending on how much mass is there. If there's more mass, the force of attraction will be larger. We can see that in the equation for the magnitude of the universal gravitational force. F-grav, it is called, is G m1 m2 over r squared. And we can go through these symbols. G is a universal gravitational constant. It's like the cosmos set that number. It's a constant number. It's like the mass of an electron or the charge of an electron. It is a value that is well known. And so that's just a constant. M1 and M2 are the two masses being attracted towards each other. There must be two masses in order for this force to arise. And of course, r is the center of mass to center of mass distance. So even if you have two objects that surfaces are touching, you can see that the center of mass to center of mass depends on the radii of both of those because it's still separated by a distance. Another thing to note about the universal gravitational force is that the direction is attractive. Things with mass attract one another. And it's on the line connecting these two centers of mass. Okay, so when you look at the radius here, the radius for these two masses would be this distance. Even though each one has its own radius, r1 plus r2, the r to be used in the gravitational force would be r1 plus r2. So watch out when it gets a little tricky with the distance between the center of mass to center of mass. Something to know is that the weight of an object is the gravitational force on an object. When we're near the surface of a planet and we know the gravitational acceleration, we can just say weight equals mg. And this is a known term for Earth, 9.8 meters per second squared. It may be different for other planets, and that's why I'm extending this to a general situation. For an object of mass on the planet Earth, this is Newton's second law. I can just set up Newton's second law and say, well, the gravitational force on it has to equal the mass times its acceleration, and I know the equation now for the gravitational force. We can see that the mass of the object cancels on both sides, and we're left with the acceleration, which we are familiar with as the gravitational constant for Earth, is this relationship, G, the universal gravitational constant, the mass of the Earth over the radius of the Earth squared. And so this can be calculated for our planet 9.8. It can be calculated for Mars. It can be calculated for the sun. It could be calculated for any object with mass. You have a gravitational field. And so that's where gravity comes from, this value for gravity comes from, and it's just from applying Newton's second law with the universal gravitational force. I will remind you of the 4-step force analysis strategy. I'm going to still keep using this. Draw the free body diagram, decompose forces if you need to, apply Newton's second law. Again, in this situation, when we're doing circular motion, we will want to put centripetal acceleration in for the acceleration term. We can solve for our unknown quantities and reflect on our answer to see if it makes sense. The problem I picked out to exemplify this first is the difference in gravity when you're on a mountain as opposed to at sea level. It says use the equation for the universal law of gravitation and the mass and the radius of the Earth to determine the exact force the Earth exerts on a person of 60 kilograms at sea level. So let's do that over here. they're just asking us to use the equation. So I'm going to write that down. F grav equals G. I'm going to have the mass of the person times the mass of the Earth. And then we're at the surface of the Earth, right? If you're at the surface of the Earth, the person will be the radius of the Earth away from the center of the Earth. And we can plug these values in. This isn't too bad. 6.674 times 10 to the negative 11th. And you can do dimensional analysis as you like in here. I'm not going to. I'm just going to plug the numbers in and know that the dimensional analysis will work out. 5.98 times 10 to the 24th power. All right, mass is a little chonky. And then I have radius squared, 6.38 times 10 to the 6th. This isn't a big mass. The mass of the sun is much larger. There's much larger objects in the universe. So when you run this through your calculator, the force of gravity in this initial situation at sea level is 588.29787 newtons. It's just a straight equation. We just used a straight equation and calculated it. So that part's done. Part B says compare this force to that of the same person on top of Mount Everest, which has a height of 8,848 meters. So when I think about Earth, right, here's the radius of the Earth. And then when this person is standing on the mountain, I'm going to exaggerate this mountain here, right? There's this additional height such that the radius, the center of mass to center of mass radius, will be the radius of the Earth plus the height of Mount Everest. That will be the radius that we'll want to put in this circle, in this equation. So when I write this out, I'm just going to use F grav again equals G, mass of the person, mass of the Earth over the radius squared. So we have G, mass of the person, mass of the Earth over radius squared. And I'm going to note in this situation again, this is going to be radius of the Earth plus the height of the mountain, quantity squared. And I can plug this stuff in, 6.674 times 10 to the negative 11th times the mass of the person, 60, times the mass of the Earth, 5.98, times 10 to the 24th. And then down here, we're going to put the radius of the Earth, 6.38 times 10 to the 6th. And then I'm going to add on this 8. How much is it? 848. There we go. Meters. Okay. We'll square that. Run that through your calculator. You get a different force, right? This denominator is different, so we should get a different force. And because the denominator is bigger, we should get a smaller force. So when you run this through your calculator, you get 586.66952 newtons. And we're seeing that the force of gravity on top of a mountain is less than at sea level. And that's because we're farther away from the center of the Earth. As you move farther and farther away from an attractive object, and because the attraction is 1 over r squared, you're going to see the force fall off as a power squared, right? 1 over r squared. Interesting fact, the difference in this force is the reason why the atmosphere at the top of a mountain isn't as dense as the atmosphere at the sea level. And you see that in cities like Denver. And when people go to climb mountains, it's harder to breathe, and that's because the pressure is different. The density of the air molecules is different, and that's because it's farther away from the center of the Earth. Very interesting force here. Let's solve a different problem involving the gravitational force, and this time let's incorporate centripetal acceleration so we can see how that works in the equations. This is a geosynchronous satellite, and they are placed in circular orbit such that they remain above the same spot on Earth at all times. So wherever it is, it's over it. And if you can imagine, the period of time for which the satellite takes to go around the Earth will be 1 day, right? So we will note that the period for the satellite's motion is about 24 hours. And we can convert that to minutes or seconds, right? We have 1 hour is 36,000 seconds, and we can convert that to seconds, 86,400 seconds. That's the period for the motion. And why did I find period? Well, I mentioned before that we have centripetal acceleration. So now I can write an expression for centripetal for the omega that goes into the centripetal acceleration. It'll be 2 pi radians over this 86,400 seconds. I'm not going to calculate this exactly. I'm just going to keep it here as I use the equations and need it in the problem. It says, at what distance above the surface of the Earth does this satellite orbit? Interesting. We can find how far above the surface of the Earth based on its period. Okay, so maybe let's just draw a quick picture of the situation just to make sure we're understanding it. Here's the Earth. The satellite is some distance away from the center of the Earth. There's the satellite. And we're going to note that the center of mass distance is going to be the radius of the Earth plus whatever distance above the surface of the Earth it will be. So I'm just going to call that h, like we did in the previous problem with Mount Everest. Okay, so that's what's going on. The satellite is feeling a single force out there. If I draw a free body diagram of that satellite, I can do that over here. Here's the satellite. The free body diagram is just F gravity. I have a centripetal acceleration towards the center of the circular motion. It goes around in a circle. So at this point, the centripetal acceleration will be inward towards the center of the Earth. And accordingly, I will assign a coordinate system such that positive, x is in that direction. I'm going to do Newton's second law right here. The net force on the satellite has to equal the mass of the satellite times the acceleration, which happens to be centripetal. The only force on the satellite is the gravitational force. I'll put this in here, G, mass of the Earth, mass of the satellite, over r squared, and that has to equal mass of the satellite times omega squared r. I'm going to note that the mass of the satellite cancels on both sides. Beautiful. I didn't even know it. Mass of the satellite, it wasn't even given. And you will see that as you move forward in physics and future topics that often the mass will cancel. Another thing I'm going to note here is that the radius is in here twice, right? R squared here, and there's an r. And that's the term sort of I want to solve for, right? So what I'm going to do is multiply both sides by r squared and divide both sides by omega squared. That'll give me G, mass of the Earth, over omega squared equals r cubed. And I'm going to write in what I know about r cubed is the radius of the Earth plus the height the satellite is cubed. So when I solve for the height of the satellite in this equation algebraically, I will get the cube root of G, mass of the Earth, over omega squared minus the radius of the Earth. Okay, that'll give me some sort of radius, and then I have to take into account the radius of the Earth. When you run this through your calculator, when you plug everything in here and you run it through your calculator, and I'm not going to do that, you can do it on your sheet of paper, but you'll see where it's going. You get the height to be 3.588 times 10 to the 7th meters, okay, which is larger than the radius of the Earth. The radius of the Earth is only 10 to the 6th, and the height above is 10 to the 7th. So it's larger than the radius of the Earth. So that's an interesting fact. So there's the height that a geosynchronous satellite is above the Earth. There's lots of satellites at that height. There's so many geosynchronous satellites, and that's where a lot of what they call space trash is as well. And they get worried about trash around the Earth, and it's because of this sort of thing they collect out there. Part B asks, what is the satellite speed? Well, let's see. I can relate speed. V equals omega r. Is that all I have to do? I'm going to note that the r here is the center of mass to center of mass distance. So we can take 2 pi over the 86400, that's the omega, and multiply by r, which is the mass of the radius of the Earth, 638 times 10 to the 6th, plus this number I just found, 3.588 times 10 to the 7th. When you find this, plug that through your calculator. Okay, it's interesting. You get this number, 3073.15441 meters per second. Of course, this is an SI, so that's meters per second. That's not as easy for me to relate to. I mean, it looks like a really large number. These satellites are flying, but they're more than the radius of the surface of the Earth away from the surface of the Earth, and they're staying in pace with the surface of the Earth, so I can imagine that they're flying through space at this large speed. And actually, when you calculate this, are you ready? It's 6,874 miles per hour. This thing is burning through space, it seems like, compared to our everyday. I mean, out in space, that's not like a large speed. But we can see that it's a large speed for us. And it helps me kind of anchor that this is the number, a number that is believable for this calculation.